There are 6 reactions of carboxylic acids that you should know, and by that I mean memorize. I want to give you an example of each of the 6, and then I'll talk about each one mechanistically a little bit, because if you understand how a reaction happens, it's easier to memorize it. You'll recognize this reaction for sure. Treating a carboxylic acid with a base removes the proton that's attached to that carboxyl group, replaces it with an ion. There's an anion, a carboxylate negative charge, that's formed. So this is a salt. Treatment of a carboxylic acid with a base forms a salt. The second reaction may be one that you saw when we talked about aromatic electrophilic substitution, because the product, this acyl chloride, is what we need to put a carbonyl group, a ketone, attached to an aromatic ring, like benzene. In any case, treatment with thionyl chloride of a carboxylic acid with thionyl chloride replaces the hydroxyl group and puts a chlorine in its place. This is the same reagent and the same transformation that we saw with alcohols, replacing an OH with a chlorine. The third reaction is one I'll talk considerably about when I talk about nucleophilic acyl substitution. In effect, taking a hydrogen away from the carboxyl group and replacing it with an alkyl group of an alcohol. Here it is. The fourth reaction is reduction. We saw the use of lithium aluminum hydride to reduce aldehydes and ketones. This is the same kind of thing, only now we're starting with a carbonyl group that also has a hydroxyl group attached. And so the reaction is a little bit different. We're replacing the carbonyl oxygen with 2 hydrogens. Here are 2 examples of the same reaction. It's really a specific case of this one that I showed you up here, the transformation of a carboxylic acid into an ester. This is the alcohol. It's part of the same molecule as the carboxylic acid group. And this OH is replacing this one. So here's our oxygen at the end. This happens when we can make a 5-membered ring and when we can make a 6-membered ring. And finally, there's a rather strange looking reaction. Here are 2 examples. When we have a carbonyl group here as a ketone or here as a carboxylic acid that is baited to a carboxylic acid, and now I'm using common nomenclature. So this is the alpha carbon, this is the beta carbon, this is the alpha carbon, this is the beta carbon, and these beta carbonyl carboxylic acids lose a whole carbon as CO2. So the carboxyl group leaves and a hydrogen replaces it. The product has 1 less carbon. These are important reactions synthetically and biologically, so we'll revisit these. These are the 6 examples that you need to learn. The loss of a carboxyl group, the formation of a cyclic ester, we call those lactones, reduction with lithium aluminum hydride, formation of esters, replacing the hydrogen with an alkyl group, making the acyl chlorides, and making salts. Let me visit each one of these briefly to say a little bit about how they happen. When you understand how those reactions take place, it's easier to memorize them. When a carboxylic acid is treated with the base, the proton is removed, and we can follow that with our typical arrow pushing. It doesn't really matter what the counterion is. It can be sodium, potassium, calcium, ammonium. It's the base we're interested in, which uses a pair of electrons to form a bond with that proton, leaving another pair of electrons on oxygen as a carboxylate anion. Recall that in theory, this is an equilibrium reaction. In practice, when we use a strong base, this forms a salt quantitatively. Treatment of carboxylic acids with thionyl chloride forms the same kind of intermediate that happens when thionyl chloride reacts with alcohols. And in the process, a chloride ion is formed. In essence, a nucleophile adds to the carbonyl as this leaving group leaves. That can't happen unless the chlorine leaves here. So ultimately, we form the acyl chloride that I've written here, plus SO2, plus HCl. When acids react with alcohols, we see the same kind of addition that we saw with aldehydes and ketones. And because this is in sulfuric acid, we can protonate that hydroxyl group. I'm shortcutting a couple of steps here that are equilibrium steps for proton transfers, and we'll talk about this more when I talk about nucleophilic acyl substitution. But rationalizing the reaction, we can think of it as a nucleophile adding to the carbonyl while this protonated hydroxyl group leaves. As the product is formed, we'll have to lose one more proton. But in terms of understanding, the essence is alcohol acting as a nucleophile, like we saw with aldehydes and ketones, to add to the carbonyl group, and a protonated water leaving as a good leaving group. We can draw on what we know about lithium aluminum hydride reacting with aldehydes and ketones to understand the reduction of carboxylic acids as well. But there's a twist or two. The very first thing that happens is loss of a proton on the carboxyl group, because lithium aluminum hydride is a very strong base as well as hydride reducing agent. And like we drew before, we'll picture a transfer of hydride from aluminum to the carbonyl carbon as the pi electrons form a bond with aluminum. But unlike the aldehyde and ketone reduction, this intermediate can lose an oxygen with the metal salts. And look what's formed. Now we have an aldehyde, and you're familiar with reduction of aldehydes by lithium aluminum hydride. So that's what happens. You have to add water to form the final product. These rings are formed the same way other esters are formed. The alcohol is part of the same molecule as the carboxylic acid. Mechanistically, it doesn't make any difference. We see the nucleophilic addition of the hydroxyl group to carbonyl. And in the process, we'll lose a proton and hydroxyl group, loss of water. So this is an intramolecular ester formation. Because it's cyclic, and you're losing water, which drives the reaction to completion, an acid catalyst is not needed. These reactions often happen spontaneously at room temperature. And finally, we can write a mechanism that lets us understand why these beta carbonyl compounds lose a carboxyl group, what we call decarboxylation. When there's a carbonyl group at the beta position, I'm writing the carboxyl group a little differently. We simply rotate it around a single bond. We can picture a cyclic movement of electrons where this oxygen becomes protonated using the pi electrons. These electrons form a pi bond between the oxygen and carbon. That forms CO2. As these electrons break that carbon-carbon bond to form a double bond. The initial product is a structure we call an enol, with a hydroxyl group attached to a carbon-carbon double bond. These guys are in equilibrium with the ketone form of that structure, where a proton has actually moved from the oxygen to a carbon. So here's a proton that is lost, was attached to this oxygen, and here's a proton that is gained, now attached to the carbon. Notice that this carbonyl group that was lost when we formed that intermediate is completely regenerated, just like it was. And that's why you see this functional group as a carboxylic acid, still a carboxylic acid. This functional group as a ketone, still a ketone. I don't think anybody will ever expect that you have memorized the details of this mechanism. But understanding something about how this reaction happens may help you memorize it. In any case, memorization is important. The facts are that a beta carbonyl carboxylic acid will lose the carboxyl group when heated. And in the place of the carboxyl group, there's a single hydrogen. So those 6 reactions I showed you in the beginning are important to memorize. Formation of a salt, an acyl chloride, an ester, reduction to make a primary alcohol, formation of lactones, and decarboxylation.